Now we want to look at more ways of building functions. We've seen named functions, we've seen lambda expressions, we've seen sections. It's where you have an operator and you provide one but not both of the arguments. So there are three ways of building functions. Let's look at one more way, and that is partial application. Now, to understand partial evaluation, I'm going to start with a meaningless function here. It's meaningless, but it's type correct. It compiles. It's been there the whole time, so you've seen it compile several times. So you can look at the shape of this function to work out what the type is. Maybe this is not exactly how Haskell does it, but it has three arguments. So we know the shape of the type has three arrows in it. The first argument goes there, and the second argument, and then the third argument, and then the result type. Okay, let's just work out the actual type. What evidence do we have to work out the types of the three parameters? We know the result is a list of some sort. So we can start by writing out the brackets for the list type. And in fact, one of the components of that result is clearly a string, because the show function produces a string. If you remember the function show, it's a thing for turning things into strings. So we know show produces a string, and therefore we know that this is a list of characters, which in other words is a string. So we know that S, the third parameter, is also a string. We know that C, which goes on the front of a string, must therefore be a character. So the first parameter, C, is a character. And the parameter B, well, we're applying the not function to it. Only thing you can apply not to is a Boolean value, and therefore it's a bool. So it takes a character, a bool, a string, and produces a string. You may have wondered now why Haskell writes functions in such a weird way. Why does it write them all with all these arrows? Why doesn't it do what other programming languages you've seen do and group all those arguments together with brackets, with commas between them? Why isn't it a char, comma, bool, comma, string, arrow, string function? The reason that they've written in this, what might seem a strange way, is in fact we can use these functions in more ways than just providing all of the parameters in order to get the resulting type of string. Let's take an example. We can apply f to a character A, the string, the Boolean value true, the string hello, and that's what it gives you. A bit of a mess, but there it is. Now, in fact, we could actually put brackets in here. We've left out the brackets that are not needed. And the reason we've done that is because essentially we can think of function application as being an invisible operation that lives between the function and its argument. And that is a left associative operator. But so if we were to put the unnecessary brackets in fact, this is what we would have. We're applying a function f to one parameter, and that's building us a new function, which we're applying to the next parameter, which is building a new function, which we apply to the final parameter. Now, we don't usually think of it that way, as being sort of several steps, but by doing so, by thinking of it as a stepwise function, we realize that we actually have a new way of building functions. Okay, just to check our understanding then, what is the type of f of a? It is a function that we've built by providing the first argument to f, which is a character, and what we get back is a function that takes two arguments, Boolean, a string, and gives us back a string. And if we apply a second argument to that function, f of a and true, we get back a function which takes a string to a string. So what that means is actually there are sort of brackets that we've missed out when we use the function, but there's also brackets that we've missed out when we write the type, and those brackets associate to the right. So in fact, what we really mean when we write a function of this type is it's a function of one argument, char, which gives us back a function. But these functions are unnecessary simply because that's the way they group, just like many operations have a default grouping. So there's more than one way of using a function like this f. Rather than just providing all of its arguments, we can provide some of its arguments and we get a function. So this is our new way of building functions that we can add to our list of recipes, and it's called partial application. We apply the function to some but not all of its arguments. And by the way, there is a notion, a simplification that this results in. Whenever we see something of the form f of x equals e of x, where e doesn't use the parameter x, that can always be rewritten, simplified to f equals e. And that's actually known as eta reduction. And when you get round to turning on the hlint for giving you hints about Haskell style, then you'll get this as a hint for simplifying your code. So in this example, if we have a function defined f of y x equals ey, then we could simplify that to f of y equals